Hello, honors chemistry students. This is Mr. Spark, and this is your Chapter 7, Section 3 notes, Bonding in Metals. So metallic bonds are based on the attraction of positive and negative charges between like atoms. And this should make sense because please remember that all metals are going to lose their valence electrons and become positive. So if you see from the diagram here, this is what a chunk of silver metal would look like. It's a bunch of silver ions with their electrons, or their outermost electrons, sort of free flowing in between the atoms of silver. And we'll talk about that here coming up. So the electron C model. Within a metal lattice, like what we're looking at here with all the silver ions, metal atoms do not share their electrons. The outer energy levels of metal atoms overlap and they form a C. So they're so packed together that their outer shells of electrons overlap. And these metal atoms donate their valence electrons to the C. And these electrons that move freely within that C are what we call delocalized electrons because they are not local. They can move around. So if you see here, and we'll look at this tomorrow in class, you see that even though we have some atoms here, these electrons are just sort of free-flowing. They don't really belong to any one atom of silver or whatever this metal may be. They just flow all around all the time. So metallic bonds are formed from the attraction of the metal cations for those delocalized electrons. So obviously the metal cations are not attracted to the other metal cations because we know that like charges repel one another. So they are attracted and held together by the delocalized electrons, sort of acting like a glue. Metals are great conductors because the electrons can flow freely in the metal. So as we, flip a switch and send some electrons through a metal wire, as electrons enter one end of the bar of a metal, an equal number of electrons must leave. So you see here, electrons are going to flow in and they can, pass all around here and flow right out. So if we send 5 in, 5 electrons are going to come out. Metals, we know, are very ductile and malleable. So ductile means that we can draw it into a wire. So as we take a piece of metal and force it through a dial, it's going to come out very thin because the atoms can slide by one another. And that is because they are malleable, which if we look over here, metals can change shape when an applied force causes layers of atoms to slip over each other. So you'll notice here, excuse me, this is the starting point, and then as we apply a force, you look at the second diagram here, and you see that they've shifted over. And they are still all held together by that glue or the delocalized electrons. So when a metal is subjected to pressure, the metal cations easily slide past one another, like what we just saw, and we can look at that here. Because again, those delocalized electrons are acting as a glue. However, in an ionic crystal, they bump into one another and the crystals shatter. So look here how the positives and negatives are lined up. But if we bump those down, if we hit them with a hammer, we might end up where the negative is next to a negative, the positive is next to a positive, and that is what causes crystals to shatter because those like charges repel one another. So the melting points of metallic compounds, overall they are moderately high, and that's because they are very tight, crowded lattice structure. However, there are of course some anomalies. For example, mercury is a liquid at room temperature or standard temperature and pressure, while tungsten melts at over 3,400 degrees Celsius. So there is quite a wide range, but overall, metals tend to have a moderately high melting point. Their boiling points are even more extreme, so think if their melting points are high, then their boiling points must be even higher. And that's because the cations and the glue of those delocalized electrons must be separated from one another. So another property is that metals are very conductive, both with thermal and electrical energy, and that's because of the sea of electrons. And the sea of electrons helps conduct heat, and it carries that electric current. Again, it's allowing those electrons or heat energy to flow through that lattice because of the delocalized sea of electrons. Metals are very hard, and they have they're very strong. The transition metals especially, we know that they have their s electrons and their d electrons, and they dump all of those into the sea of electrons because they have so many of them. The more electrons in the sea, the harder and the stronger the metal. So as you move across a period, they are typically harder and stronger. Think about the alkali metals in group 1. They are very soft. Remember whenever I cut those just with a scupula, and then if we go over to the right, we end up with something like zinc, which we'll look at in a lab today. It is a very hard, rough metal. So metals do have a crystalline structure. We will not spend too much time talking about these. So just the names and the shapes are important. So they are very highly ordered arrangement of atoms. So the body-centered cubic, here are some examples. We have sodium, potassium, iron, chromium, and tungsten. And you'll see here that it's just quite simple. It's a cube, and then on the body of the cube, or the faces, it has an atom on the left and an atom on the far side as well. So this is what it looks like in a diagram overall. So this center atom has 1, 2, 3, 4, 5, 6, 7, 8 neighbors. And when metals have this structure, they tend to look like this. Face-centered cubic is another one. Here we're looking at metals like copper, silver, and gold. You can see that it's a little more beat up, I guess, a little more malleable. Looks like you can manage its shape a little differently. Here we have about 12 atoms. Then the last one that we'll talk about is hexagonal close packed arrangement. This is for those messier elements like zinc. You can see the shape of it is not very uniform at all. But you'll see it's given that name because of the hexagons that create the outer edges of the crystal lattice. So hexagonal close packed. Last thing we're going to talk about is alloys. Alloys are just a mixture of 2 or more elements of at least one of which is a metal. So brass is an alloy of copper and zinc, and brass is typically used to make instruments. Alloys' properties are often superior to those of their component elements. For example, sterling silver is only about 92.5% silver and 7.5% copper. It is much harder and much more durable than pure silver. Pure silver, you could crush it very easily. The most important alloys today are steels, and you can see all of the component elements that make up steel. Steel is very corrosion resistant, it's very ductile, it's very hard, and it's very tough. So for example, nail clippers, also think about the school that's being built. That is all steel beams. These alloys can form in many different ways. If the atoms are about the same size, they can replace each other in the crystal. This type of alloy is called a substitutional alloy. So think about, on a sports team, somebody goes and substitutes in for somebody else. It's just like that here in the crystal lattice of a metal. However, if the atomic size is quite different, the smaller atoms can fit into the interstices or the spaces between the larger atoms. This type of alloy is called an interstitial alloy. So right here, look, we have a pure metal. All the atoms are the same. Here we have a substitutional alloy. So you see that this second metal has replaced some of the original metal atoms to give us a nice mixture or an alloy. And then over here on the right, all of the original metal atoms are there. And these smaller metal atoms, they're so small that they just fit in between all the spaces. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, resources CD, and pearsonchem.com. Have a great day.